You don't have to drug them in yet if you don't want to. All right. So guys, I'm happy about the fact that most everybody got the Z-score kind of problems correct. Because we're going to, I think I told you this, Z-scores dominate almost the rest of the class, except for the last kind of stuff we do, correlation and regression. We'll get there. The very next thing we're going to do is something called confidence intervals. So, if somebody told me, if I needed a part and it had to be a certain size, but I could tolerate it being a little bit off, right? I want to know. I want to set up some kind of a. How do I want to say this? Let me do this. So let's say, let me come a different way. Say the age at Grossmont. There's a certain average age. It's somewhere out there. There's a certain true average age. And when I say true, I mean population average age. If I take a sample, let's say I take a sample of size, I don't know, 50. But I take 50 Grossmont students completely at random. Beautiful sample. It's a beautiful sample. What should be true about the sample mean? If I took a nice random sample of 50 people, what should be true about it? Should be close to the population mean. I like it. I think it's maybe what some of you guys other muttered. So it could be down here, it could be up there. So let's say I just happened to take some people that were younger. Just randomly happened. So there's my sample mean. So what we're going to do is, what happens most often in statistics is I have no idea what the real average is. I go take data to try to figure out what it looks like it might be. So if I want to know what's the average longevity, the average number of years that a coyote lives out in the wilderness, what am I going to do? I'm going to have to go out, get a sample of coyotes, watch them until they pass away, and then keep track of the data as how long they live. Do you guys have to collect all the data? Do I have any idea how long they live on average? Can I ask one of them, hey, coyote, how long do you guys live on average? There's a gnawing on my foot. It's no good. Do you guys, so very often we're investigating things, we have no idea what it is, and I can't get a hold of the entire population of coyotes. I just can't do that. I can get a sample of coyotes, tag them, follow them, so forth, and then I want to try to say something. So I'm going to get an average age of a coyote at death, and there's a real average age that I'm trying to estimate. So what I'm going to do now is, I'm also going to get, let's say that I happen to know, and this is going to be true at first, let's say that I don't know sigma, but I do know, I don't know mu, but I do know sigma. How does that sink in? It seems very strange. But let me give you an example of how this could be true. So let's say there's an area in Wyoming, or Minnesota, let's do Minnesota, because I know there's coyotes up in Minnesota, where some company has been dumping stuff, and I want to see how it's affecting the coyote population. So I know information about all coyotes. We've done past studies. So I know what this is from the past study, but I don't know what this is for the subgroup of coyotes that are affected by this illegal dumping of whatever, this pollutant stuff. Are you guys with me? So this isn't so impossible that I don't know what this is, but I do know what this is because it could be a subgroup of a larger group. So let's say that I think in a town there's something with the water that's making the people there grow shorter than normal, right? Some water is stunting their growth, right? Or the coffee's just too strong or something, I don't know. You guys still with me? So I know the standard deviation of heights for men and women in the U.S. I know this, but I don't know the average height in this little area, this town, or this little part of the state. Do you guys follow? So, what do we do in statistics? We get the best thing we can, which is a sample mean. But now I'm going to try to use that sample mean to estimate what this guy might be. A little better than just saying, I think it's close to this. Ooh, that's some good lightning. Sorry. Total San Diego boy now, missed by lightning. Oh, that's too bad for you. It's good to be the teacher. You can hear that. Yeah. Oh, yeah. Very strange for this area. All right. You see if I can possibly compete with lightning. All right, guys. Hey. All right. So what I do is I calculate this. Right. I take a sample. I calculate this. I know this. So let me ask you this. And what I do then is, guys, hey, I build this what we call a confidence interval. I go up and down so much. It sounds familiar to things we've done so far. Like to find the max usual and min usual, I add and subtract 2 standard deviations. So we're going to do something very similar to that, except it's not always going to be 2. It depends on how confident I want to be. All right, so this is one thing. Whenever I teach this, there's always several things they just got to throw at you, and it doesn't really matter what order I do it in. So here's one thing. Here's the idea. This is really the idea behind what we're going to do. I'm going to make an interval, find a simple mean, somehow construct an interval around it, and then say something like, I am 98% confident that the real mean is in there. That would be something kind of powerful to tell somebody. There's only a 2% chance I'm wrong, so that's better than normal. All right, there's that idea. Here's the other idea. This is something we can do immediately without too much explanation. Let's see how right the statement is. Can you guys tell me if the mean of something was, what is it, 27. Standard deviation was 3.8. Can you tell me between, say this. We took a sample of size, let's start here. Oh my God. The mean is 27. Guys, it's not the easiest thing in the world to figure out how to tell you. So the mean is 27, the standard deviation is 3.8. Can you tell me between what two values would there be 9, let's go with 90, let's go to 90%. Let me tell you this also, it's normally distributed.
That's hard.
Oh my God, was that a fart joke? What'd you say? Alright, so can you guys do this? It's normally distributed. Mean of 27, standard deviation is 3%. Between what two values would there be 90% of the data? So if you draw the picture, I want between two values to be 90%. So let me help you out a little bit. Yes. So let me help you guys out if you have any trouble. How do I find the z-scores that these are? I've got to do that first, right? I've got to go from percentage to z-score, and then I can use this bad boy here to change it back into an actual data point.
So it's going to be the middle
The middle 90%. Sure.
Good.
Good. So the chart doesn't have a clue about this number at all. The chart only understands areas that are where? Below. So I want two z-scores. What's going to be true about these two z-scores? Because it's the middle 90%. They're going to be opposites of each other, right? If one's -2, the other's going to be 2. So if I can figure out this z-score, I know both of them, right? So what area do I use to get that z-score? 0.05. So we look that up. What's z-score? Should be one that's an asterisk. Like it, negative 1.645, so what's the other one? 1.645. I like it. So this is all, this here is old news. I could have asked you this question. There was one like this on the practice test. Right? Find the z-scores bound in the middle 90%. So now how do I convert it back to data points? Look at each other. So basically this becomes, do you guys understand why I wrote this? 27 plus or minus 1.645 times 3.8. Because they're going to go up 1.645 and down 1.645 steps. And each step is 3.8 big. So if I go that far out, I'm guaranteed to catch 90% of the data. Let me let that sink in. If I didn't go out that far, I would catch the same amount of data. If I went out this far, maybe up 1 and down 1, would I catch the same amount of data? So if I went up to here and down to here, would I catch the same amount of data? No, of course not, right? Smaller net, I catch less fish, right? I don't catch as much data because I only went up and down that much. So for a 90%, so if I would have made this 99% instead, do you think that this number would have been bigger or smaller? If I would have made this 99%, what would happen to this? It would push it out, so these would get bigger positive, bigger negative. I got to go further out to catch more data. I don't have to go as far to catch less data. Let that part make physical good sense. All right. So now, what's the connection between this business and that business? Well, this sounds something like what I want to do there. The big difference between this and that is here I don't know this. I've only got this. So that's kind of a huge difference. Also, how would I get this? What does this stand for? Sample mean. So I must have taken a sample of size something. Therefore, what's going to have to change? Standard deviation. I like it. You were just ahead of it. Right. Clairvoyance. All right. So here's how this is going to look. So here's what a problem's going to look like. I could say, we take a sample of the map. 47 coyotes. And find X bar equal to 4.19 years. Sigma is known to be 1.74 years. So here's the part that's new. What we call this kind of thing, what I'm going to create, I'm going to do exactly what we did here, except the standard deviation is going to be different just because I took a sample. Is that cool? Otherwise, everything's exactly the same. So I would call this thing, I would call this a confidence interval, 90% confidence interval. So the whole idea here is there's a real mean somewhere. I take an X bar, I build this interval, And then I am that confident that I caught the real mean. I'm that confident that that confidence interval has the mean in it. Because how much data did I catch? I would catch, well, haven't told us yet, no. I would catch whatever percentage I want. It's going to change my z-score. It's going to be far enough out so I catch that much data. So then I'm that sure that I caught any specific value. So there's a mean that exists. My sample mean is probably not going to be the same, but it should be pretty close. If I took a random sample. So then if I build this interval, if I want to be 99% confident that I catch the real mean in that interval, I'm going to make my interval big enough to catch 99% of all the data. Then I'm, of course, 99% sure that I caught the real mean. So here's what it looks like work-wise. Let's see, find the... Let's do a 95% confidence interval. So first step is, how the hell do we find a 95% confidence interval? We'll do the same thing we did here. So when I say confidence interval, it means catch the middle whatever percent, whatever that confidence I want to be. So I want to be 95% confident, so I want to catch the middle 95%.
Are you going to tell us it's normal? Or
Yeah, what is it about this problem that I don't have to say it's normal? Why do I know that my population of all samples are going to be normal enough? Yeah, the sample size is big enough. I like it. Good point, though. Don't feel that's a perfect point. So that's why I had to say it over here, because I didn't take a sample over here. I like it. So who's got those z-scores? What are you going to look up? What's in this tail here? 0.025. I like it, because there's 5% outside. There must be 2.5% on one side. Some of you guys might even notice at the bottom corner of one side of the z-score chart, there's something called confidence levels. I call it the baby confidence level chart. If you look at the one for 90%, doesn't it say 1.645?
Yeah.
Oh shit! And if you look at the one for 95%, it says 1.96. I like it. Because if you did look up 0.025 in the body of the chart, you would see negative 1.96. So they've collected the most commonly used, 95% is the most commonly used confidence interval level. Just because. And why does that make sense? Because it relates to how far out do I go to find unusual? 2 standard deviations, and that catches 95% of the stuff for a normal distribution. So that's the most commonly used one, but it depends on the situation. So this will be negative 1.96. Positive 1.96. That's how far out I have to go to catch 95% of the information. So if I translate those back to years, then I'm going to be 95% confident that my interval catches the real mean. That's the whole idea. Why am I that confident that it catches the real mean? Because it catches 95% of all the data. Yes, sir?
is the z-score the answer? Or?
No. My answer's got to be, I'm trying to capture the real average age at death of these coyotes, how long they live. So it wouldn't make any sense to say negative years. They died way before they were born. It's horrible.
So find the x in there.
Yeah, I got to convert those back to an x score. I like it. So for this one, it would be, actually, again, I can write this like this. Now watch this. It's going to be what now? It's going to be x bar plus or minus 1.96 sigma. I'm going to start at x bar as my best guess for the real mean and go up and down 1.96 standard deviations. So it'll be 4.19, give or take 1.96 of these.
Since it's a sample, do we have to...
Oh yeah, thank you. In the formula, it's going to be this guy. So what's the square root of, what's the n here? 47, yeah. So you have to change that. So that's the difference between this problem and that problem is this problem, there was no sample taken. So I didn't have to change the standard deviation. That one I do. So see if we can get this part here. Let's analyze this thing real quick. 4.19, give or take 1.96 of these. This part here is called the error. This, of course, is we sometimes call this the point estimate. I always see that as just saying our best guess. Our best guess in any situation is going to be the mean that we see. So what's our best guess for the average age of coyotes in this area? 4.19 years. It's our best guess because that's the average we saw. So we're just making our guess a little bit better by saying, okay, it's somewhere close to 4.19 years. And why does it make sense to call this the error? Because that's how far off we think we are. We think it's this, give or take that. So this part's going to be how far off we think we are. So if you pay any attention to the election, if you see the polls, very often at the bottom we'll have candidate A is 42%, candidate B is 37%, and what's at the bottom is a plus or minus 4%. This plus or minus, when we do this kind of problem for percentages, that's where they calculate that from. It's not just let's make it plus or minus 4% to cover our ass. It's actually based on how big the sample was, how big the standard deviation was. That's what goes into figuring out that plus or minus number. So help me out. What do you guys? So normally when I tell people is calculate the error first, because then you can just add it to this and subtract it from this. So did anybody do the error? Normally you take this out one more place than this is. All right, so this is 2 places. I'm going to take this one out 3 places. So now you just do 4.19 minus this and 4.19 plus this. Please don't ask me where the plus or minus key is. Right, it's 2 different things. Some of you guys look, but it's happened to me before, so. So based on what we see, we can say with 95% confidence that this interval will catch the real mean. Now, the semantics of it connects with the idea of it. You don't want to say that I'm 95% confident that the real mean is in this interval. And I know it's like stats is hard enough already, don't bring semantics into it, but that makes it sound like the real mean is just going to fall somewhere. The real mean exists, it's just sitting there, waiting. It's like, somebody find me. The real mean is just sitting there. And so you go and you take a sample, and you make a confidence interval around yours. Somebody else goes and takes another sample, and makes a confidence interval around theirs, and so forth. If I got enough people, if I got a lot of people do confidence intervals, then at 95%, then 5% of them would not get the real mean. Let me stop there for a second. If I'm 95% confident that my interval contains it, then what's the chances that it doesn't? 5%. So if 10 people, let's say 100 people, did a confidence interval for this, for the coyote's age, then I would say 5 of them, about, would not have it in their interval. So the right way to say this, I can tell in your eyes you love this already. You're going to love this last part because you have to write me a statement. Or not, if you don't want to get the points. That's always an option. I'm okay with failing. We are farmers. No, we are 95%. Every time I say it. Dun, 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 dun. We're 95% confident that the interval, what to what? What does this mean? What is this? 3.693 years to 4.687 years contains the true mean length of life of these coyotes. You're going to have to write that kind of statement for me. And that's really interpreting the numbers you find from your analysis. So every time you see a poll for anything, they very rarely tell you what they used to calculate the poll. How confident what level of confidence did they use? How many people did they talk to? That's very often missing. All of that tells me how much to trust or not trust with it. If they made an 80% confidence interval, screw them. There's a 20% chance they're wrong. I'm not going to look at that crap. So most confidence intervals you see are actually 95%. So there's a 5% chance that that's wrong, right? So people think that means that it's definitely in there. Well, no, this could very well be wrong. There's so many freaking polls out there, it's almost impossible for none of them to be wrong. So some of them are wrong. Okay. Like it. Alright. So let me formalize the formula to use for this. Let me try to show you a connection with the formula we've used in the past. So in the past we've done this. We did this earlier. I put the plus or minus in there because it's basically what we did earlier. But we know mu plus z sigma. That gives me x, right? So we've done this in the past. So if I don't know this, I take a sample and use this. But since I took a sample, what has to happen to this? So that is the formula for a confidence interval for a mean. There's going to be a formula for the confidence interval for a proportion that's going to be related to the plus or minus 4 percentage points you see on polls. All right. So let's do another one. Say again? So let's say take a sample of 58 stat students. Find a mean number of Tylenol taken per day. Let's say per week. Equal to 20.79. Sigma is known to be what you got? 4.111. Yeah. I don't know that because so they're going to have to give you all this information. And then they're going to have to tell you one more thing. Find the blank percentage confidence interval. If it's one of the ones on the little baby chart, you can use that. It's awesome. But of course, I'm not always going to do that. So find the 96% confidence interval. CI is now confidence interval for the true mean in this problem. So give it a try. As far as you can. Using that formula. What do you have? What did I tell you that's in there? What's the only thing I didn't tell you? Z-score. And where did you get that from? How confident you want to be. Alright, do it. Attack it. You got everything you need except one thing. Once you get that one thing, it's a plug and chug. nice to believe.
Let me come in and not get their test back.